It's only the third time in human history that we've spotted something from deep space wandering into our solar system. But this isn't just any visitor. This one is acting like nothing we've ever seen gliding through our celestial backyard. Imagine an object hurtling past our planets at mind-melting speeds, carrying mysteries from a region of the galaxy that no telescope has ever glimpsed in such intimate detail. You might have seen a few headlines about this latest interstellar arrival, but tonight we're going to push far beyond the surface-level buzz. We're peeling back the layers to uncover the strange, almost unsettling details astronomers have been whispering about, the kind of discoveries that keep them glued to their data long after midnight, running calculation after calculation that stubbornly refuses to align with the models in their textbooks. Welcome back to The Weary Researcher. Tonight we'll dive into a cosmic enigma so rare and so baffling that it has the brightest minds in astronomy, both exhilarated and deeply unsettled as they try to understand what exactly we're witnessing. Before we launch into the mystery, I'd love to know where in the world, or perhaps what time of night, it is as you're watching. It's always fascinating to see our community of stargazers spread across every corner of Earth. And if you find yourself drawn to these deep space riddles, these delicate unwrappings of the universe's most guarded secrets, I'd truly appreciate it if you tapped that like button and joined us for more explorations. Our story starts quietly, without warning, on a seemingly ordinary summer morning, as July 1st, 2025 unfolded. In the hushed, windswept deserts of Chile, a telescope caught sight of something extraordinary, a faint, almost forgettable speck crawling across a field of stars. Yet the data told a different story. The tiny point of light was racing at a staggering 130,000 miles per hour. This wasn't another routine asteroid from our solar system, nor a common comet lazily drifting along. No, its path, its speed, and its origin screamed of the vast, cold emptiness between the stars. It was an uninvited guest from the abyss of interstellar space, and even in the first hours of discovery, it began challenging everything scientists thought they understood about such rare cosmic wanderers. Most reports about what's now called 3I Atlas have only brushed the surface. Yes, it's fast, record-breakingly fast. Yes, it's from beyond our star system. And yes, it's the third confirmed interstellar object in the history of humankind. But those facts are just the skeleton of the story. Tonight, we're chasing the flesh and blood of it, the irregularities in its motion, the strange traits it displays that seem to mock our expectations, and the wild range of theories from the mundane to the almost unthinkable about what it could be. The deeper astronomers look, the stranger it appears. After weeks of relentless tracking, one fact has crystallized. Atlas is not obeying the unwritten rules we thought these objects followed. The first chapter of this puzzle began in the early hours under the sharp, high-altitude skies of northern Chile. The discovery came courtesy of the Atlas telescope, that's short for Asteroid Terrestrial Impact Last Alert System, in Rio Hurtado. The telescope forms part of a NASA-backed network, its job to scan the heavens for objects that could one day pose a threat to Earth. But on this particular night, its gaze fell on something far less dangerous and far more captivating. Right away, its motion set it apart. Astronomers across the globe took notice, and within a single day, eyes from 3 continents were locked on this peculiar visitor. Observations came pouring in from the Deep Random Survey Telescope in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope atop Mauna Kea. What they were watching wasn't a wandering speck of rock from the outer solar system. It was an interstellar trespasser, only the third ever identified. Its name, 3I Atlas, tells you its rank in this exclusive group. The 3I marks it as the third interstellar object, putting it in rare company with the cigar-shaped Oumuamua spotted in 2017, and Comet 2I/Borisov in 2019. But in almost every meaningful way, Atlas is rewriting the rulebook for these kinds of discoveries. One of the first to study it in detail was Colin Orion Chandler from the NSF DOE Vera C. Rubin Observatory. His team pieced together data from June 21st through July 7th, even uncovering earlier images that had been quietly storing the object's light in databases before anyone connected the dots. The analysis suggested a nucleus of roughly 5.6 kilometers across, give or take 700 meters, far bulkier than Oumuamua and on par with Borisov's size. But size alone wasn't the headline. Its brightness was peculiar. At an absolute V-band magnitude of about 13.7, Comet was shining in a way that hinted at more than just bare rock or ice. Patterns in how it reflected light suggested a cloak of dust, not a thin veil but rich, abundant clouds of it. And that pointed to something interesting about its structure or history. NASA's Transiting Exoplanet Survey satellite, better known as TESS, provided earlier snapshots that let astronomers trace its activity even further back. Those observations only deepened the mystery. Atlas wasn't just breaking the speed records for past interstellar guests. It was gliding along a path that happened to sit unusually close to the flat plane in which our planets orbit. The ecliptic, well, typically, visitors from deep space plunge in along steep, angled trajectories, like celestial spears cutting through the planetary plane. Atlas, by contrast, is moving with an orbital tilt of less than 5 degrees. That puts it almost side by side with the paths of Earth, Mars, and Jupiter, an almost eerie alignment so unlikely by chance that it's raised immediate speculation about where it came from and how it got here. The shape of its journey adds another layer of intrigue. Atlas is on a hyperbolic trajectory, meaning it's moving fast enough not only to escape the sun's pull, but to continue on into interstellar darkness once it's gone. Its orbit isn't a repeating loop but an open arch, the hallmark of an outsider just making a pit stop before being forever flung back into the vast unknown. Comparisons to the two earlier visitors are inevitable and revealing. Oumuamua was a riddle wrapped in a metallic, tumbling shape, with no comet-like halo, yet an unexpected acceleration on its way out of the solar system, as if pushed by an invisible hand. Borisov, in contrast, played to type, a classic comet sprouting a glowing coma and tail, showing off its ice under the sun's heat. Atlas, though, Atlas refuses to fit either mold, leaving experts unsure if they're looking at a cousin of these earlier travelers, or a completely different category altogether. Under the microscope, Atlas sat in a strange middle ground, not a textbook comet like Borisov, not a puzzling dry oddball like Oumuamua, and that's where the real intrigue starts to build. Early spectra delivered a head-scratcher, instead of the strong chemical fingerprints you'd expect from gases boiling off an active nucleus. The dominant signal leaned toward fine dust and a subtle reddening of the reflected light, hinting at a cloud of tiny particles surrounding the core rather than the usual balanced mix of gas and dust, seen in classic cometary comas. That detail clashed with its obvious activity, since images already hinted at a faint haze and even a nascent tail, suggesting something was driving material away from the surface, despite the muted gas signature. The first reactions were cautious. Veteran observers like Dr. Alan Hale, known for co-discovering Hale, BOP, initially reported no clear gaseous lines, which sparked debate and a flood of follow-up campaigns. As fresh observations rolled in on July 2nd, just a day after the official flag went up, the picture shifted. Teams operating the Deep Random Survey Telescope in Chile, the Lowell Discovery Telescope in Arizona, and the Canada, France, Hawaii Telescope on Mauna Kea captured consistent evidence of a delicate coma and the early outline of a tail-like extension, confirming that the nucleus was venting material. The object wasn't dormant, it was alive with activity, just not in the way everyone expected. That's when Hubble stepped in and changed the resolution of the story. With a kind of clarity ground observatories can't match, the Space Telescope resolved a lopsided, teardrop-shaped shroud of dust wrapped around the nucleus rather than a neat, symmetric glow. That asymmetry hinted at uneven heating, surface jets with preferred directions or complex topography controlling how particles escaped. By tracking Atlas cleanly in long exposures while background stars streaked, astronomers pinned down its position with razor accuracy, tightening orbital solutions and sharpening inferences about where it came from and where it's headed next. Then came the breakthrough that reframed the early confusion. NASA's Neil Gehrels Swift Observatory, designed for high-energy transients, turned its ultraviolet eyes on Atlas and caught unmistakable signatures of water vapor lofted around the object. That detection confirmed active outgassing of H2O, implying subsurface ices were warming and venting as sunlight intensified along its hyperbolic path. Beyond settling the is it a comet? Question. This provided a first chemical fingerprint of material forged under a different star, a rare window into exoplanetary system chemistry without sending a probe across the gulf. Swift's result also explained why initial spectra seemed reluctant to show gas. Earth's atmosphere absorbs key ultraviolet wavelengths, and the object's distance and faintness made those lines hard to catch from the ground. Once space-based UV data arrived, the missing piece snapped into place. The gas was there, but subtle, and the instruments that could see it weren't the ones first on the scene. Even so, fresh riddles emerged. Follow-up campaigns expected to snag telltale signals of other common volatiles, carbon dioxide and carbon monoxide, which often drive activity at larger heliocentric distances, yet those lines remained elusive. Typical comets in our neighborhood release a cocktail of ices that sublimate under sunlight at different thresholds. But Atlas appeared selective, with water taking the lead and the usual CO or CO2 tracers oddly quiet. That imbalance raised questions about formation temperatures, long-term irradiation, or evolutionary processing in an alien protoplanetary disk. Was this body forged in a warmer region? Has its surface chemistry been altered by eons in interstellar space, or is dust concentration masking some emissions? Rotation only added layers to the puzzle. Analysts inferred a spin period on the order of hours, but nailing down the exact cadence and the pole orientation proved slippery. That's not unexpected with interstellar travelers. They move fast, brighten quickly, and zip through the inner system in a window that closes before campaigns can converge on a full solution. Variations in activity can also bias light curves, and jets can fake brightness modulations that look like spin signatures, making disentanglement tougher. At this stage, the narrative took on a more daring edge. Harvard astrophysicist Avi Loeb, no stranger to controversy after proposing that Beaumanoir might be artificial, examined the early Atlas data with a willingness to test unconventional angles without abandoning rigorous checks. In work co-authored with Adam Hibbard and Adam Krell from the Initiative for Interstellar Studies, he catalogued anomalies that didn't slide neatly into standard comet behavior, focusing on what photometry and astrometry seemed to whisper between the lines. Several points stood out. First, the dust-to-gas balance looked skewed in the initial window. Dust dominated earlier than expected at Atlas's distance, unusual if typical volatile-driven jets were in charge. Second, its track through space, already uncanny for its near-ecliptic alignment, showed small deviations that could hint at uneven outgassing or internal restructuring, as if different vents pulsed at different times or the surface shed material in bouts. Most provocative was the way it seemed to respond to non-gravitational forces. Comets often experience subtle trajectory nudges as jets act like miniature thrusters, the rocket effect, yet Atlas's measured response looked off-pattern, producing what Loeb described as anomalous photometric and astrometric behavior that resisted easy parametrization. Crucially, this line of argument wasn't pitched as a leap to sensationalism, but as a set of hypotheses to be weighed against expanding datasets. The straightforward reading acknowledged by Loeb is still the leading one. Atlas is a comet, and the earliest measurements undersampled its gaseous output due to distance, instrument limits, and atmospheric constraints. As higher fidelity observations rolled in, the water detection, the asymmetric dust cocoon, that conservative model gained traction. Still, the door remained ajar for surprises. If ongoing tracking continued to reveal dust production that refuses standard scaling laws, if trajectory adjustments can't be reconciled with plausible jet models, or if the volatile inventory stays oddly selective despite increasing solar input, then the case for something more unusual would strengthen. That something doesn't have to mean artificial origin. Nature offers many ways to craft oddities. Thermal fracturing on layered crusts can switch jets on and off. Organic rich mantles can suppress certain emissions while amplifying dust release. Past close passes by other stars or shock processing in dense interstellar clouds might bake in behavior unlike anything born in our own system. But the willingness to test edge case hypotheses serves the science. Push the models against data, refine the parameters, and see what survives. For now, Atlas sits at the intersection of expectation and anomaly. It emits water, carries a dusty shroud that isn't symmetrical, hugs the ecliptic in a statistically rare alignment, and shrugs at some of the non-gravitational patterns seen in local comets. Its spin is likely fast but not yet pinned, its chemistry selectively loud, its dust-to-gas story evolving as it draws nearer to the sun's warmth. Each night of observations sharpens or softens earlier claims, and with every refinement, the object either steps closer to familiar physics or leans further into the weird. That tension is what makes this visitor so compelling. It's not just another icy body paying a brief visit. It's a messenger carrying a complex past written in grains, vapors, and trajectories. A riddle that might update how we think about the materials and mechanisms shaping small bodies beyond our sun. If the next wave of data locks in the conventional reading, we'll have our first detailed chemical case study of water-bearing ices from another stellar nursery. If not, the mystery deepens, and the hunt for an explanation, natural or otherwise, will only grow more urgent. The discussion surrounding Atlas wasn't unfolding in a vacuum. Astronomers had already weathered one very strange chapter back in 2017 when Oumuamua baffled the scientific world. That object had accelerated slightly as it left the sun's vicinity, a measurable push without any visible jets or detectable gas to explain it. Many eventually leaned toward theories involving exotic outgassing of hidden hydrogen or other unconventional natural processes, but the case cracked open a door that allowed more adventurous speculations about what interstellar intruders could be. So when Harvard's Avi Loeb floated the idea that Atlas might also be something unusual, the backlash from peers came fast. Dr. Jason Wright of Penn State, a researcher well versed in both natural and possibly artificial space phenomena, publicly disagreed. In a post on his blog, AstroWright, Wright pointed out that just 11 days after the find, Loeb was already suggesting an artificial origin on the basis of slim early spectroscopy that showed dust reddening but little obvious gas. Wright stressed that the early phase of comet observation almost always shows dust dominance, particularly when an icy body is still far from the sun and hard to study due to faintness and high speed. He argued that the absence of immediate gas lines wasn't an anomaly at all. It was a limitation of the observational window. Others backed that view. Dr. Michelle Bannister, an expert in distant solar system bodies, reminded the community that interstellar objects present unique hurdles that can easily skew early interpretations. Their velocities are extreme, the time to observe them in detail is short, and their faintness pushes even large telescopes to the limit. At the heart of the Atlas debate was an ongoing struggle in astronomy, how to handle rare phenomena that offer incredible scientific value but require conclusions to be drawn under severe time pressure. When a discovery captures global headlines, as the prospect of alien technology inevitably does, the tension between scientific caution and public excitement only intensifies. Meanwhile, the work went on at a relentless pace. Observatories worldwide tightened their coordination to extract every bit of knowledge before Atlas slipped away. The European Southern Observatory's Very Large Telescope in Chile began tracking its brightness and dissecting its light to better understand its composition. The Gemini facilities in both Hawaii and Chile launched a detailed campaign to map coma development and watch for the growth of a tail. Perhaps the most ambitious effort tackled one of the hardest problems, retracing Atlas's steps across the galaxy to guess its birthplace. Astronomers traced its incoming trajectory backward, attempting to pinpoint a home star system. It's an exercise riddled with pitfalls. Star motions shuffle over millions of years, and tiny velocity errors balloon into enormous positional uncertainties across light years. Nonetheless, early backtracking suggested this traveler had wandered the void for countless millions of years and likely entered from the direction of Sagittarius, a stellar-rich patch toward our galaxy's center. Statistically, many random visitors could appear to come from that direction simply because the stellar density is so high, but more refined modeling revealed something that made Atlas stand out. Most interstellar objects slice into our solar system from random angles, but Atlas seemed almost too well aligned, cruising close to the ecliptic plane, the flattened disk where our planets orbit. The chance of that happening naturally was low, hinting that the comet's route might have been shaped by past gravitational nudges from other stars or planetary systems on its long voyage. That convenient alignment carried a bonus for Earthbound observers. Atlas would remain within view far longer than the steep diving visitors of the past, giving astronomers a rare extended window to gather measurements. As days passed, the data pile grew thicker. Swift's ultraviolet detection of water vapor was verified by follow-up observations that pinned down the rate of outgassing with greater precision. Hubble kept refining the picture of the asymmetric dust shell, revealing subtle shifts in how particles clustered as sunlight worked its way deeper into the surface. On the ground, California's Palomar Observatory used its 200-inch Hale telescope to capture high-resolution images of what formed into a short, stubby tail. Nothing like the sweeping arcs of familiar comets, but a modest plume that signaled comparatively gentle activity. Spectroscopy, too, began digging deeper. Instruments that had originally only caught dust-induced reddening now teased out faint absorption patterns, identifying specific molecules. Water remained the loudest signal, and there were tentative detections of hydroxyl radicals, the dissociation products of water ice under solar UV bombardment. What continued to baffle researchers was what they didn't see. No clear signs of carbon monoxide or carbon dioxide, compounds abundant in many homegrown comets, and typically the first to vaporize well before water ice begins to flow. This absence hinted at more than a fluke. Perhaps Atlas formed in a stellar nursery very different from our Sun's, one where planet-building chemistry leaned toward water-rich but CO-poor ices. Stars of different sizes, ages, and elemental makeups forge planetary systems with unique chemical profiles, and comets from such systems could carry fingerprints alien to our usual samples. Alternatively, Atlas's long drift in the interstellar deep freeze might have stripped certain volatiles from its surface, leaving a body rich in water ice but depleted in CO and CO thal. Either way, it meant that what was drifting past our Sun wasn't just rare because of its origin. It was chemically distinct, a messenger with a composition unlike anything regularly found in our own backyard. It opened a thrilling possibility. Atlas might be our clearest look, yet at the raw chemistry that shapes planets in another star's nursery, not through theory or distant spectra from disks, but from material drifting right past our Sun. Another angle was just as compelling. The space between stars is unimaginably cold, only a few degrees above absolute zero, yet it isn't quiet. Cosmic rays and high-energy particles pepper small bodies for eons, slowly reworking their surfaces, molecule by molecule. Over millions of years, that kind of radiation can drive off delicate ices and alter what remains. If Atlas spent ages in that harsh, silent environment, it could have lost the most fragile volatiles long before arriving, leaving behind a mix dominated by water ice, mineral grains, and a stubborn dust mantle. That interpretation made sense on paper, but it collided with another reality. Atlas resisted neat labels, where 2I/Borisov behaved like a model comet. Textbook coma, predictable tail, abundantly clear volatiles. This newcomer defied easy reading. Its brightness flickered in ways that didn't slot into simple outgassing models, and its spectral fingerprints seemed to shift subtly from night to night. Some of that came down to logistics. At roughly 130,000 miles per hour, nothing we've studied from beyond the Sun's realm has moved faster, and speed is the enemy of deep spectroscopy. Long exposures smear, signal fades, and the window for precision work narrows by the hour. Add to that the object's faintness, and suddenly only the largest mirrors in pristine conditions could deliver usable data at all. Yet even after correcting for those hurdles, Atlas didn't align with familiar categories. It wasn't inert and puzzling like Oumuamua, which kept its jets hidden while still accelerating away. It wasn't a straightforward ice and gas show like Borisov, either. It sat between those poles, clearly active, but on its own terms, expressing an unusual balance of dust, water, and faint or missing signatures of typical volatiles. A personality that sidestepped the templates astronomers lean on when time is short and data is patchy. That ambiguity quickly became the core of a lively and sometimes heated debate. The conservative camp argued that the oddities would shrink as observations improved. Better signal, broader wavelength coverage, and more time would reveal a normal interstellar comet, perhaps a bit bigger and faster than average, but fundamentally ordinary. They pointed to a long track record in astronomy where early anomalies evaporate under the light of better data. Others leaned into the possibility that the differences were real. Maybe comets forged in other stellar systems truly carry different inventories of ices and organics. Maybe long interstellar transits toughen and transform these bodies in ways we're only beginning to recognize. And then there was the boundary-pushing idea. Controversial, yes, but not dismissed out of hand by everyone, that a subset of interstellar visitors might be engineered rather than natural. The artificial origin argument, promoted by Avi Loeb and collaborators, rested on more than a single spectral quirk. They pointed to the near-ecliptic arrival path, the selective outgassing profile, where water showed up, but CO and CO thighs stayed elusive, and the object's reluctance to fit standard non-gravitational force models. Taken together, they argued, those features could hint at intentional design, or at least an unconventional structure. They framed it as a hypothesis, not a conclusion, but the ramifications were enormous. If Atlas were a probe, it would be the most consequential discovery humanity has ever made. It would confirm that intelligence arose elsewhere and mastered interstellar operations, raising difficult questions about purpose, communication, and the possibility that other devices pass through unnoticed. Most researchers pushed back hard. Extraordinary claims demand extraordinary evidence, and the cluster of Atlas anomalies, they argued, sat comfortably within natural explanations for a body with unfamiliar composition and a long, cold history under relentless radiation. Astronomy's archives are full of once baffling patterns that faded into routine, once instruments sharpened and theories matured. The Martian canals turned into optical artifacts. The steady-state universe gave way to expansion and a hot Big Bang. Over and over, mysteries became mundane as measurements improved. To many, Atlas felt like another chapter in that tradition rather than a break from it. The broader context of SETI made the conversation even more nuanced. For decades, searches for signals from distant civilizations have run quietly in the background, producing no confirmed detections. The notion that the first clear sign of technology would be a passing object, not a beacon, intrigued many, but also looked statistically awkward. If a civilization were deploying probes widely, the argument goes, we should see far more traffic, not one oddball every few years. The appearance of Oumuamua in 2017, Borisov in 2019, and now Atlas, spaced out by years, seemed more consistent with natural ejections sprinkled through space than with a systematic survey program by an advanced species. Advocates of the engineering hypothesis countered that the statistics are paper-thin. 3 detections do not define a frequency, especially when the discovery tools are new and biased toward the brightest, dustiest, and most conveniently placed visitors. Smaller or darker interstellar travelers could have slipped through unnoticed for generations. Confirming interstellar origin requires tight orbital solutions, which take time and precision. Some past passers-by might have been misfiled as local asteroids or comets before their hyperbolic nature became clear. So the clock ticked, and the race to learn as much as possible began to outrun the object itself. Atlas had whipped past its closest approach to the Sun by late July 2025 and turned outward, growing dimmer and more distant each day. Observers shifted strategies, trading deep spectral ambitions for broader coverage across wavelengths, stacking shorter exposures and coordinating handoffs between hemispheres to chase every usable hour of darkness. Each data point stitched another thread into a complex tapestry. Water unequivocally present, dust wrapped in an asymmetric shroud, a short and modest tail, brightness fluctuations that hinted at uneven heating or rotating jets, and a chemistry that stubbornly held back CO and signatures even as solar energy should have teased them out. That pattern sharpened 2 competing narratives. In one, Atlas is a natural comet from a different stellar nursery, born in a region where water-rich but CO-poor ices dominate, or altered by interstellar radiation that preferentially stripped more volatile ices over millions of years. In the other, Atlas carries unusual structure or materials that modulate outgassing in non-standard ways, producing trajectories and brightness behavior that slip past simple comet models. The first narrative fits the history of science, where oddities gradually find a home in expanded frameworks. The second refuses to die because the object keeps dodging easy boxes. Regardless of which scenario wins, Atlas has already rewritten the playbook for how to chase these rare visitors. The whole enterprise now hinges on faster alerts, rapid multi-wavelength follow-up, and cross-continental coordination that turns nights into continuous coverage arcs. And looming over the horizon is a facility likely to change everything: the Vera C. Rubin Observatory in Chile. Once it comes online, it will sweep the entire visible sky every few nights with a cadence and depth unmatched by current surveys. That tempo won't just increase the odds of catching interstellar bodies, it will transform discovery into routine. Instead of one object every few years, astronomers anticipate dozens, possibly hundreds, per year when conditions align, capturing faint travelers that today would slip by without a ripple. With that flood will come the statistics needed to move beyond anecdotes. If most interstellar visitors share Atlas's selective chemistry, we'll know that foreign planet-forming regions commonly produce water-forward, Colorado-Nyssa-like comets, or that interstellar exposure sculpts them in predictable ways. If near-ecliptic arrivals turn out to be more common than theory predicts, we'll look harder at gravitational shepherding across the Milky Way. If non-gravitational forces repeatedly misbehave relative to standard jet models, the physics of porous ices, complex mantles, and subsurface pockets will get a major overhaul. And if even one object shows patterns that survive every natural explanation, the technological hypothesis will move from the fringe into the center of the table. For now, Atlas recedes, still enigmatic, still whispering rather than shouting. It may never give a final verdict on what it is, but it has already delivered something arguably more valuable, a blueprint for how to study the next ones, and the ones after that, with urgency and rigor. The greatest lesson might be patience. These objects don't lend themselves to instant answers. They require layers of observation, careful modeling, and an openness to revise assumptions without leaping to extremes. If the coming era of sky surveys fulfills its promise, the next interstellar messenger won't just be a singular mystery. It will be one data point among thousands, each carrying a fragment of other worlds' histories. And somewhere in that growing archive, the story we've been trying to read in Atlas's flickering light will finally come into focus. The avalanche of discoveries expected from next-generation surveys promised the statistical heft needed to decide whether Atlas was a rare outlier or simply part of the normal spectrum of interstellar travelers. Meanwhile, researchers squeezed every last photon of data they could from this fleeting cosmic guest. Even spacecraft not built for comet chasing joined the hunt. The European Space Agency's Gaia mission, famous for mapping the positions and motions of stars with breathtaking precision, pivoted to lock its sensitive detectors on Atlas. While Gaia's prime task was stellar cartography, its ability to spot the tiniest perturbations in position could reveal subtle twists in the object's path, clues to its interior makeup or the way its surface responded to sunlight. NASA's James Webb Space Telescope, humanity's most capable infrared eye in space, also entered the campaign. Webb's thermal vision was tailor-made for unraveling the heat signature of Atlas and searching for molecules invisible to optical scopes. With it, astronomers hoped to resolve one of the great puzzles, the missing carbon compounds. They also aimed to build a far more complete chemical inventory, molecule by molecule. On Earth, planetary radar teams tried their luck, despite daunting odds. Atlas's speed and growing distance made it a poor radar target, and the loss of Puerto Rico's legendary Arecibo Observatory in 2020 had removed one of the world's strongest beacons. Still, what remained, NASA's Goldstone facility in California and the radar capabilities at Green Bank, West Virginia, were pushed to their limits in the hope of catching even a faint return echo from the departing object. Each fresh dataset added to the mosaic, but the overall picture stubbornly refused to settle. Some observations backed the conservative view. Atlas behaved like a comet, venting water as the sun's warmth penetrated its surface. Others reinforced curiosity. The dust-to-gas ratio leaned heavily toward dust. Only selective volatiles were escaping, and its details kept slipping away under closer scrutiny. The intrigue was fertile ground for public fascination. On social media and in science outlets, theories, both grounded and speculative, circulated with lightning speed. The idea that humanity might be watching an alien probe, while far from proven, gripped imaginations everywhere. And it wasn't only professionals contributing to the chase. Skilled amateurs, armed with advanced CCD cameras and computerized mounts, tracked the tiny dot across the heavens. Their gear lacked the raw sensitivity of billion-dollar observatories, but their strength was persistence. Night after night around the globe, they added vital continuity, a long-term light curve here, a positional refinement there, building bridges between the larger but more sporadic professional observations. This citizen science backbone underscored one of modern astronomy's most profound changes. The boundary between professional and amateur has blurred. With the right tools, passionate individuals were helping decode the mysteries of an interstellar interloper. Teachers and professors quickly recognized the object's educational goldmine. Students were introduced to Atlas not as a static textbook entry, but as a live unfolding case study in how science works when the rules aren't yet written. Classes tracked real-time updates, examined data releases, and debated competing hypotheses, seeing firsthand how collaboration, skepticism, and evidence intersect in the scientific process. The project was inherently multidisciplinary. Astronomers examined orbital mechanics, planetary scientists modeled thermal processes, chemists interpreted spectral lines, and physicists explored how solar radiation might interact with dust-laden surfaces. All this demanded international coordination on a scale rarely seen for a single small body. Atlas's rapid migration meant observers had to pass the target from one longitude to the next in a precisely choreographed relay. Chilean night skies handed off to Hawaii and California, followed by observatories in Europe, each catching their window before darkness moved on. Linking this global chain was no easy feat. Telescope time is fiercely competitive, often booked years ahead, yet the urgency of Atlas's transit led to schedules being reshuffled, observing nights reassigned, and long-planned programs set aside. Behind every beautiful spectrum or crisp image lay the price of power-hungry technology, expert staff keeping instruments tuned, and hard calls on how to spend finite research budgets. For most in the field, the investment was worth it. Even if Atlas proved to be a plain interstellar comet, the dataset it left in its wake would be unlike anything compiled before. Detailed composition profiles would feed directly into models of how planets form in alien star systems. The confirmed presence of water ice suggested the processes building icy planetesimals in our own solar system occur elsewhere, a linchpin fact for gauging the ubiquity of habitable conditions. Since water is a cornerstone ingredient for life as we understand it, finding it frozen within a body that began life around another star hinted at a galaxy where life's raw materials might be scattered far and wide. Just as important were the differences. The stubborn absence of carbon dioxide and carbon monoxide, assuming it wasn't just a detection gap, pointed toward diversity in planetary system chemistry. Such variations carried weighty implications for how planets evolve and what chemical environments life might emerge from. On the dynamical front, mapping Atlas's galactic voyage promised insights into the gravitational traffic patterns between stars and how frequently these frozen messengers swap neighborhoods. Perhaps less visible to the public, but just as significant to scientists, were the broader technical gains. Methods honed to track fast, dim, hyperbolic objects could be deployed the next time on an asteroid skimming Earth, a wayward comet, or the next visitor from deep space. Protocols for global coordination, once a logistical experiment, had now been tested in the fire of real necessity. When the next transient spectacle appears, and it will, the community will be faster, sharper, and more connected for it. Atlas may yet fade into the anonymous dark, its mysteries only partly resolved, but it will leave behind a transformed playbook for planetary science and interstellar studies. In the end, even if the answer is just a natural comet, its brief encounter with our sun has expanded our scientific reach, tightened our networks, and deepened our sense that the galaxy is an open system, one where materials and perhaps someday messages can flow between stars. Under the harsh light of limited data, astronomers leaned on every analytic tool they had, stacking short exposures to beat motion blur, cross-calibrating instruments across observatories, and applying statistically robust models to pull weak signals out of noisy backgrounds. And those same methods will strengthen work on other hard-to-catch targets, from dim near-Earth objects to transient outbursts in the outer solar system. Yet the greatest legacy of Atlas may be less about technique and more about perspective. It reminded us, powerfully and personally, that our solar system is woven into a much larger tapestry, with matter and possibly messages drifting between stars over spans of time, far longer than human history. Whether Atlas proves conventional or remains stubbornly odd, its presence marked a tangible physical link to distant worlds, with its ices and dust carrying a record of formation under unfamiliar suns and in alien chemical environments. That duality, practical science on one side, philosophical resonance on the other, brought something deeply human into focus. The public's intense interest in a technological origin revealed how strong the yearning is to confirm we are not alone. In contrast, the slow, careful posture of professional inquiry highlighted a different strength. The discipline to separate desire from evidence, to keep fascination from steering conclusions. Wonder sparks the questions. Skepticism secures the answers. Atlas sat right at that junction, inviting imagination while insisting on rigor, refusing to surrender meaning without proof. As the initial excitement cooled, the real work began, the meticulous, unglamorous process that turns scattered snapshots into a coherent understanding. Teams gathered spectra from multiple epochs and instruments, correcting for atmospheric absorption, instrument response, slit losses, and telluric lines before fitting models that disentangle overlapping molecular contributions. Photometric time series were normalized, phase angle effects removed, and rotational light curves probed for periodicities that might hint at spin state, surface heterogeneity, and jet-driven modulation. Astrometric positions were reprocessed against refined star catalogues to tighten non-gravitational parameters and isolate subtle accelerations from outgassing. Each step demanded cross-checks, re-reductions with independent pipelines, blind tests on synthetic data to quantify biases, and careful propagation of uncertainties so that downstream inferences didn't overstate confidence. The early outcomes were encouraging without being definitive. Water activity was solidly confirmed, cementing Atlas's status as an active body warmed by sunlight. Dust properties, grain sizes, porosity, scattering behavior began to look less exotic once models assumed formation conditions, distinct from the solar nebula, with compositional tweaks that alter reflectance and thermal inertia. Orbital refinements trimmed the space of sensational trajectories, undercutting some of the more speculative dynamical scenarios proposed in the first days, but the thorniest puzzles held fast. The selectivity of outgassing, water present, while carbon monoxide and carbon dioxide stayed elusive, resisted simple explanations. Brightness variations kept hinting at complex behavior that didn't cleanly match a single rotating, uniformly venting nucleus. And the provenance question, which birth system, what path through the galactic tide, which encounters nudged it onto this near-ecliptic arc, remained open-ended despite improved kinematics. Those sticking points were more than academic. They exposed the edges of today's toolkit. Measuring the size and shape of a faint, fast mover at long range pushes the limits of both resolution and signal-to-noise. Determining the spin pole demands dense, well-phased light curves rarely possible for a hyperbolic sprinter. Interior structure can only be inferred indirectly, from thermal response, from how jets alter motion, from sublimation rates that depend on unknown porosity and layering. Compositional diagnostics rely on the coma, not the nucleus itself, and can be skewed by dust masking, photodissociation cascades, and line-of-sight geometry. These realities argue for something bolder than incremental improvements, a new playbook for interstellar targets. That next playbook is already being drafted. One strand imagines space telescopes dedicated to fast movers, wide-field, rapid-cadence platforms tuned to ultraviolet through infrared bands, where key volatiles reveal themselves, able to pivot within hours of an alert and stack clean, atmosphere-free spectra before the object fades. Another strand is more audacious. On-call spacecraft waiting in heliocentric parking orbits, fueled and flight-ready. On detection, mission control uploads a burn plan, and within weeks a compact interceptor is on a flyby trajectory, carrying a minimal but decisive payload. Narrowband UV, IR spectrometers for volatiles, a dust analyzer for grain composition, and size distributions, and high-speed imagers to resolve the nucleus and jet sources. Such missions demand high-thrust, high-Ruth capability, autonomous navigation to chase an unpredictable target, and an engineering culture comfortable with rapid deployment and limited lead time. But the science return would be transformative: direct imaging of the nucleus, in situ dust chemistry, and unambiguous volatile inventories. Space agencies are sketching variants of this vision. Studies examine staged architectures, a mothership bus launched in advance with multiple daughter probes, each capable of a close pass, hybrids that combine solar-electric propulsion for crews with chemical stages for the final sprint, and small sat swarms that bracket the object from multiple angles to reconstruct jets and mass loss in 3D. Trajectory design is its own frontier, balancing time of flight against encounter geometry, so instruments hit the right phase angle for plume backlighting and thermal mapping. None of this is trivial, but the challenge is proportionate to the prize. On the ground and in orbit, AI has become an indispensable ally. The data torrents from survey telescopes overwhelm classical pipelines, and interstellar visitors won't wait for manual vetting. Machine learning models trained on millions of labeled detections now flag hyperbolic candidates in near real time, prioritizing follow-up. Computer vision tracks faint streaks and rapidly moving point sources across crowded fields, reducing false positives and salvaging objects that would have slipped through. Spectral classifiers, tuned on ensembles of comets and asteroids, can separate dust-dominated continua from weak volatile lines, estimate water production rates from blended features, and assign confidence scores that guide which targets warrant precious telescope time. Reinforcement learning optimizes scheduling across networks of observatories, sequencing exposures to maximize global coverage under shifting weather and visibility. The Atlas campaign sharpened all of these tools, not as abstract demonstrations but as systems tested against a moving, fading, and scientifically urgent target. Perhaps the most instructive lesson wasn't technical at all, it was organizational. No single observatory, agency, or nation could cover Atlas end-to-end. Success depended on a relay of facilities across longitudes and latitudes, with handoffs timed down to minutes. That level of coordination confronted non-scientific obstacles: budget constraints, rigid time allocation systems, differing priorities and processes, language barriers, time zones, even occasional geopolitical friction. And yet, curiosity proved adhesive. Teams shared ephemerides, calibration frames, reduction scripts, and provisional fits. They synchronized wavelength coverage to avoid duplication and staged simultaneous observations to capture multi-band snapshots. Amateur networks filled temporal gaps, sustaining long baseline monitoring while large telescopes executed deep dives. The enterprise looked messy from the outside: rescheduled nights, emergency proposals, instrument swaps. But it worked, and it built trust for the next sprint. Even if Atlas ultimately lands in the natural comet column, its scientific dividends are already substantial. Quarter activity ties the chemistry of other star systems to our own, reinforcing the idea that life's foundational solvent forms widely in planet-forming disks. The atypical volatile profile, if confirmed, broadens the map of possible chemical starting points, implying that planetary systems span a spectrum of ice inventories and dust chemistries, outcomes of different stellar metallicities, disk temperatures, and irradiation histories. Dynamically backtracking its path, even imperfectly, feeds models of how small bodies exchange between stellar neighborhoods, how often ejections occur, and how the galactic tide and passing stars sculpt those routes. Methodologically, the field now owns better algorithms for astrometry and photometry under duress, tighter protocols for intercomparison of instruments, and a clearer sense of which observations deliver the most leverage per minute when time is tight. There's also a cultural imprint, a recalibration of how we talk about uncertainty in public. Atlas became a case study in balancing openness with rigor, acknowledging tantalizing anomalies without overstepping the evidence, exploring high-risk hypotheses while stating their low prior probability, updating conclusions in real time as data improved. That transparency matters. It shows that science is not a collection of instant proclamations, but a process that tolerates ambiguity, converges through iteration, and grows stronger by inviting critique. Looking ahead, a maturing ecosystem could turn rare opportunities into routine science. Rapid alert networks broadcast candidates within minutes. Q-scheduled telescopes bake in flex time for urgent targets. Space-based assets maintain standing modes for fast movers, with pre-validated command sequences that minimize turnaround. Interceptor concepts progress from paper to hardware, beginning with pathfinders that practice close passes on known comets to validate navigation and sampling at high relative velocities. In parallel, survey cadence accelerates and detection thresholds drop, building the statistical archive needed to answer the looming questions. Do most interstellar comets share Atlas's selective chemistry, or did we meet an outlier? How common are near-ecliptic arrivals, and what does that say about long-haul gravitational shepherding? Are non-gravitational perturbations consistently atypical, or do they settle into patterns once rotational states are nailed down? With dozens to hundreds of detections, those answers transition from speculation to measured fact. The philosophical horizon broadens alongside the technical one. If a future visitor refuses every natural explanation after exhaustive testing, the conversation about technology will move from speculative to evidentiary, a profound shift with implications for policy, communication, and ethics. If instead, the catalogue fills with diversity rather than singularity, we gain something just as grand, a map of how many ways nature can build small worlds, each a capsule of its home system's conditions. Either outcome elevates our understanding and situates humanity more accurately within the galactic context, not as isolated observers, but as participants in a slow exchange of material and knowledge across astronomical distances. Atlas, in that sense, is a teacher disguised as a question. It taught how to coordinate better, analyze faster, and communicate more carefully. It reminded us that patience is a scientific virtue, that rigor and imagination are not enemies but partners, and that progress happens not in viral moments, but in the accumulation of careful, revisable work. As it fades into the dark between stars, what remains is a stronger framework for the next encounter. Sharper tools, tighter networks, and a refined sense of what to ask when the next faint, fast dot appears on a screen and dares us to find out what it is. And when that moment arrives, we'll be ready to move sooner, see deeper, and decide smarter. The lesson of Atlas is clear. The universe will keep sending opportunities. It's on us to meet them with discipline, creativity, and humility, to let wonder pose the questions and let evidence write the answers. The media storm that surrounded Atlas brought another challenge into sharp relief: the difficulty of translating complex science into language the public can grasp without losing nuance. In the early days, headlines fixated on the flashiest possibilities: alien probes, unexplained anomalies, tantalizing hints of mystery. Lost in many of those stories was the quieter but equally remarkable work of establishing the object's most basic characteristics: its trajectory, its chemistry, its interaction with sunlight and space. For the astronomers actually studying Atlas, the balancing act was constant. They had to acknowledge where the evidence was still thin, correct misconceptions without dampening curiosity, and resist the urge to deliver quick, overly simple answers when real understanding would take months or years. That gap between the speed of the news cycle and the pace of science was a constant source of friction. People wanted definitive answers now. The reality was that conclusions would arrive slowly, built layer by layer, as new data joined what came before. Social media amplified both the promise and the pitfalls of that engagement. On the bright side, platforms like X and YouTube gave scientists a direct line to global audiences. They could share fresh images within hours, explain a finding in their own words, and invite skilled amateurs to contribute their own measurements. But the same channels also became vectors for misinformation, fueling conspiracy theories about cover-ups and alien visitation that spread as fast as, and sometimes faster than, solid science. The tightrope for researchers was keeping the public engaged while defending the guardrails of scientific skepticism. Inside the astronomy community, Atlas also sparked deeper conversations about priorities and how resources should be spent. Chasing this fleeting visitor demanded a massive diversion of telescope time, staff hours, and funding, all of which meant putting other projects on hold. No one doubted the scientific goldmine that interstellar objects represent, but some argued that the balance was off, that such effort might be more wisely invested in deep, systematic sky surveys that could reveal many objects instead of an intense campaign on just one. Others countered that every interstellar traveler carries a unique fingerprint of the system it came from, and that a detailed portrait of even a single visitor could be invaluable, knowledge that might not come again for decades. The debate captured a broader, perennial tension in astronomy: sweep wide for breadth, or drill deep for detail. By the time autumn edged closer, Atlas was well on its way out, its distance stretching, its glow ebbing. Each week that passed pushed it further toward invisibility, and soon even the most capable telescopes would lose it entirely to the backdrop of stars. The race for last light observations became intense. Every exposure mattered. Cameras with long integrations pulled out faint ghosts of its coma. Ultra-sensitive spectrographs strained for molecular whispers buried in the noise. By September 2025, Atlas had dipped below the reach of most observatories. Only a handful of the world's largest instruments could still pick it out, and even they struggled. The campaign that had dominated the field for months was winding down. With no fresh photons coming in, the research shifted gears. All that frantic collection would now be distilled and tested, the chaos of fieldwork giving way to years of careful synthesis, simulation, and peer review. Early consensus leaned toward Atlas being a large, fast interstellar comet, with uncommon composition and an unusual thermal history. Its release of water and display of comet-like activity strengthened that interpretation. Many of the oddities, from its dust signatures to its selective venting, seemed within the reach of natural explanations tied to its alien birthplace and the difficulty of the observations. But there were stubborn edges that refused to smooth out. The precise cause of its chemical selectivity was unresolved. Its dust makeup didn't match the solar system norm, and it continued to resist the kind of clear-cut categorization scientists prefer. A few researchers held on to the view that it might represent not just a rare type of natural body, but something entirely new, whether a category of comet never seen before or something stranger. The argument likely wouldn't end soon. As the data was revisited, models would evolve, and new perspectives might shift once solid assumptions. Each run through the analysis could reveal overlooked signatures or close off earlier interpretations. In a way, Atlas's legacy was already bigger than the identity question itself. It had been a catalyst, forcing advances in rapid response observing, tightening the mesh of international collaboration, and creating unprecedented public participation in real-time astrophysics. It had stress-tested the infrastructure of modern astronomy, making plain both its strengths and its soft spots. And it reinforced an idea more profound than any single hypothesis. Our solar system is open to the wider galaxy. Atlas arrived as a tangible reminder that planets, comets, dust, and perhaps even messages can wander between stars on million-year journeys. Every interstellar object is a physical connection to an origin we have never visited, a messenger shaped by conditions utterly unlike our own. If Atlas was just a comet, it still carried in its core the chemical record of a planet-forming disk around another sun. The discovery also lit a fire under the search for more such messengers. New survey programs were proposed and existing ones upgraded, with improved detection pipelines that leaned on lessons from tracking Atlas. Algorithms were tuned to flag fast movers with unusual orbits earlier, giving follow-up teams more time before they faded. The Vera C. Rubin Observatory, rolling toward its operational debut in 2025, stood poised to change the game entirely with a panoramic high-cadence watch on the sky that might spot dozens or even hundreds of interstellar objects a year. That torrent of detections would finally let scientists answer the statistical questions hanging over Atlas. Is this what typical looks like, or did we witness something exceptional? Space agencies were rethinking mission design to meet that coming wave. ESA's Comet Interceptor could be retargeted if a suitable candidate appeared. NASA engineers explored rapid response spacecraft concepts that could launch within months of discovery, intercepting these visitors for close-up study before they slipped away again. On the ground, upgrades to instruments and adaptive optics systems promised sharper images of faint, distant targets, while spectrograph redesigns aimed to pull out clear chemical fingerprints during the narrow window. these objects are observable. Atlas may be gone from our sky, but it left behind a blueprint, both in the data it carried and in the way it tested the readiness of science to react. It expanded our awareness of the galaxy's reach into our own neighborhood, reminded us of the interplay between wonder and evidence, and underscored that each fleeting visitor is an opportunity to see far beyond the boundaries of home. One of the most important takeaways from the Atlas story was how critical pre-discovery data could be for unlocking the secrets of interstellar visitors. Weeks before anyone realized what it truly was, Atlas had already been quietly captured in routine survey images. Those early frames proved gold, giving astronomers the extratemporal baseline they needed to sharpen its orbit, refine its velocity, and piece together its behavior well before the spotlight found it. This lesson was quickly absorbed. New automated pipelines were spun up to comb through archives hunting for missed interstellar migrants, with the potential to double or even triple the known population almost overnight. The spirit of ad hoc, round-the-clock cooperation that had sprung up during the Atlas campaign was now being formalized into permanent infrastructure. International agreements and protocols were drafted to ensure that when the next truly strange object appears, the response will be instantaneous and globally coordinated. Secure, real-time communication channels now link observatories across continents, ensuring a sighting in one hemisphere can be acted on within minutes in another. Public engagement, another defining chapter of the Atlas experience, was also evolving. Researchers had learned how to better explain uncertainty, how to convey the patient, iterative nature of science without draining away the excitement that draws people in. Educational packages were being created to walk non-experts through how astronomical research actually works, why the process takes so long, and what makes careful analysis different from speculation. Citizen science programs were expanding to actively involve amateurs in detection and tracking, not just as spectators but as contributors. Advanced analysis software, once the domain of professionals, was being opened to the public, putting cutting-edge tools in the hands of a growing global network of engaged observers. The campaign had even rippled into economics and technology policy. Investing in telescopes, data pipelines, and international cooperation had proven its worth, not just for studying comets, but for developing methods that could be applied in other sectors that require fast, sensitive detection and rapid decision-making. And perhaps hardest to quantify, but just as real, was the surge of curiosity Atlas inspired. A discovery this enigmatic reached audiences that routine astronomical findings never touch, igniting the imaginations of students, enthusiasts, and future scientists, while boosting support for education and research. By the close of 2025, the visitor was retreating rapidly toward the depths between the stars. Even as its coma thinned and its light dimmed, its influence on human understanding was still expanding. A steady stream of papers poured into journals, tackling every angle from its chemistry and grain makeup to its intricate gravitational history. Some teams dove deep into the trajectory, trying to rewind the celestial clock to locate its birthplace and chart gravitational nudges along the way. Others explored what Atlas means for our theories of how planetary systems form and evolve, and whether such wanderers might even play a role in transporting life's building blocks from one star system to another. The more speculative thread of the conversation, the idea that Atlas might be artificial, lingered, though most in the scientific mainstream remained unconvinced. Avi Loeb and his collaborators published detailed arguments highlighting the object's unusual traits, while other researchers countered with analyses showing those same observations could arise naturally. It was science functioning as it should, bold ideas meeting rigorous testing, with both sides driving the data toward more solid ground. Still, public opinion diverged from consensus. Surveys showed a sizable fraction of people believed in the artificial origin scenario, despite the absence of proof. The gap between popular belief and scientific caution underscored the ongoing challenge of teaching how science actually works. Atlas, meanwhile, was seeping into popular culture, appearing in novels, documentaries, and classrooms worldwide. It had become a symbol of cosmic mystery, representing our restless drive to push the borders of what we know. By the time the first anniversary of its discovery arrived in July 2026, the frenzy of observations had ended. The giant scopes that could still glimpse it would keep doing so for only a short while longer. Attention shifted fully to the painstaking work of analysis and interpretation. By then, a provisional picture had emerged. Atlas was most likely a large interstellar comet, enriched with some uncommon traits shaped by its birth environment and perhaps its long exile in interstellar space. Many of the early mysteries, including its puzzling spectra, were clarified with better data. Its path and overall behavior fit comfortably within natural explanations. Yet unanswered questions remained. The fine details of its composition were still murky. Its internal structure was invisible. Its origin star was unknown, and a few subtle observational quirks continued to defy easy categorization. Still, its place in scientific history was already assured. Atlas had propelled advances in technology, methodology, and global cooperation. It reaffirmed that our solar system is not sealed off, but part of a web that spans the galaxy, with material and perhaps even signals drifting between stars over astronomical timescales. Every such visitor is an opportunity to learn more about that network and our role in it. While astronomers turned to their archives and simulations, the search for the next interstellar envoy was already humming. Automated survey systems swept the night sky for telltale hyperbolic paths. Machine learning classifiers trained on the patterns. Atlas left behind scanned detections in real time to flag the most promising candidates for immediate follow-up. It was now a matter of when rather than if. The next time an interstellar traveler appears, the world will be ready, faster, better organized, armed with the hard-won lessons of Atlas to wring every bit of science from its brief visit. And hanging in the air was a question that only the future could answer. What would the next one be? Another enigma to puzzle over for years. A more typical comet offering clear evidence of alien planet-forming chemistry, or something that would eclipse even Atlas in its strangeness. The first undeniable artifact of another civilization. For now, only time holds the answer. It felt inevitable. Every new traveler from beyond the sun has the power to reshape how we see the cosmos and our place within it, and Atlas was no exception. Brief in our skies, but huge in impact, catalyzing advances in technique, coordination, and the scope of our questions. Even if its full story remains unsettled for years, as with Oumuamua before it, that lingering uncertainty is part of the value, a reminder that the universe still outruns our models and invites better tools, better data, and better ideas. In that sense, Atlas did exactly what science asks of a mystery. It forced sharper methods, inspired global collaboration, and drew new minds into the work, proving that curiosity and rigor can coexist with the patient's real understanding demands. But to grasp why Atlas stands apart, it helps to zoom in on the technical signatures that have kept experts at the whiteboard. Classic comets brighten in a fairly predictable way as solar heating ramps up. More sunlight, more sublimation, more reflective dust, and a photometric curve that roughly tracks the inverse square intensification of insolation, modulated by geometry and the details of a comet's activity. Atlas deviated from those expectations in more than one dimension. Its near-ecliptic arrival was statistically unusual for a random interstellar passerby. It raced in on a strongly hyperbolic orbit with high excess speed, and its early spectra leaned dust-heavy before space-based and infrared work confirmed water-driven activity, a sequence that complicated the usual brighten with heating narrative seen in well-behaved solar system comets. Pre-discovery coverage became the backbone of the analysis. Rubin's commissioning images captured Atlas days before the official alert, tightening the orbit and showing that a coma was already present, while test recovery indicated it was active even farther out, implying volatiles beyond water were likely in play at larger heliocentric distances. Those constraints matter for photometry. If the object was already venting before the discovery window, simple brightness, distance relations can mislead unless activity history and viewing geometry are baked into the model. Early ground-based spectroscopy found a dust-dominated, red continuum with no strong gas bands at several Al, consistent with many comets at that distance. Yet Hubble soon imaged an asymmetric, teardrop-shaped dust cocoon, a morphology that points to directional jets or uneven surface heating, rather than a neat, symmetric coma. That asymmetry can imprint subtle, non-monotonic trends in the light curve, as jets rotate in and out of view, masking any naive inverse square expectation. Then came the pivot, ultraviolet observations, with NASA's SWIFT detected OA emission, a proxy for water vapor, confirming active water release at a surprisingly large distance, which is unusual but not unprecedented, and suggests either efficiently exposed water sources or icy grains, lofted into the coma, acting as extended reservoirs. Near-infrared follow-up and broader context reinforce that picture, while Hubble imaging helped bracket the solid body's size to a few kilometers at most, with many analyses favoring a smaller nucleus obscured by dust. Together, those lines of evidence explain why a straightforward photometric slope could look off-model, an interstellar comet already active far out, with selective volatiles, asymmetric dust release, and line-of-sight geometry changing rapidly as it hurtles inward. At tens of comma cells will not map neatly onto a classroom light curve. On top of that, Atlas's specific kinematics matter, with a hyperbolic excess velocity on the order of 58 kilometers per cell relative to the Sun and no future return. Small outgassing-driven forces can alter its sky path and apparent brightness with phase angle effects that evolve fast, especially near the ecliptic, where observation cadence was intensive. Time series suggested little short timescale variability at discovery epochs, a hint that either the nucleus light curve was damped by a steady coma or the spin geometry minimized observed modulation. But that still leaves room for longer period or jet-driven changes that skew nightly, photometry away from simple heliocentric distance laws. Put differently, Atlas's light didn't just scale with how much sunlight it received, it scaled with what parts of its surface were active, how dust production evolved, how grains scattered light, and how our vantage point lined up, a complex, evolving 4D problem. All of which is why Matthew Knight's kind of analysis, long experience with comet photometry and the discipline to separate geometry from physics, is essential to decode what the light curve is really saying when an interstellar object doesn't behave like a standard template, with precovery imaging anchoring the baseline, Hubble's morphology clarifying coma structure, and Swift's OAG detection setting the volatile floor. The emerging picture is coherent even if it's not yet complete. Atlas is an active interstellar comet whose dust first appearance gave way to confirmed water outgassing at large distance, whose asymmetric coma and unusual arrival geometry complicate simple brightening laws, and whose nucleus is likely on the smaller side of early estimates. Once the coma's contribution is properly discounted, that complexity is precisely the point. Objects like Atlas aren't just samples from other suns, they are stress tests for our methods. They force photometry to account for grain physics, spectroscopy to chase faint lines under hostile geometry, orbit models to incorporate subtle non-gravitational terms, and coordination networks to move from alert to multi-wavelength coverage in hours, not weeks. Whether Atlas turns out to be chemically typical for its birthplace or something rarer, the tools forged in its wake, Rubin precoveries, space UV water diagnostics, rapid HST morphology, and public-ready explanations that don't overpromise, will determine how well we read the next message from the deep. What Knight uncovered shook some of the most basic assumptions about how an interstellar object should behave. Atlas's brightness record wasn't the smooth, predictable curve of a rotating body venting evenly into space. Instead, the light output pulsed unpredictably, sudden surges in luminosity that lasted a few hours, then collapsed back to baseline. He called them brightness bursts, like flashes from a cosmic beacon, scattered throughout the observing window with no obvious pattern in timing or strength. The result was a light curve that had more in common with a variable star than a garden variety comet, and that alone pushed traditional comet models beyond their comfort zone. Even after factoring in odd nucleus shapes and patchy surface activity, the standard explanations fell short. The complexity grew when spectroscopy joined the fray. Dr. Sees Binning Yang at the European Southern Observatory mounted a full spectrum assault with the VLT's X shooter, one of the most sensitive instruments of its kind, spanning near UV through the near-infrared in a single shot. The result was the most detailed chemical profile ever captured for Atlas's coma, and it refused to fit into the catalogue of any comet in our database. Water vapor was present, yes, but the chemistry around it was skewed in ways no one had seen before. The water-to-hydroxyl ratio was off the charts. roughly triple the standard value, hinting at unusual dissociation processes or ice structures that trapped and released water in unfamiliar ways. Carbon monoxide, normally a dominant volatile at the temperatures and distances Atlas was crossing, was barely detectable at all. Stranger still, the spectra contained clear signs of silicon-bearing molecules, rare in comets, but characteristic of material that has endured high temperatures or intense radiation. That pointed to two possibilities. Atlas had been thermally processed somewhere in its past, or it was born in an environment utterly unlike the outer cold zones where comets in our solar system form. The dust carried its own secrets. Using polarimetry, a technique that measures the orientation of light waves after they scatter from particles, Dr. Jessica Agarwal at the Max Planck Institute for Solar System Research was able to read the fine structure of Atlas's dust grains in ways no simple image could. Her results were startling. The grains were exceptionally small, averaging just 0.1 microns, about a tenth the wavelength of visible light, and they scattered light in a pattern never recorded from a comet before. Many of them appeared crystalline in structure, a telltale of formation in high-temperature environments. That was at odds with the frigid birthplace most comets call home. Meanwhile, Hubble's sharp eyes revealed a coma unlike the billowy, largely symmetrical envelopes we're used to seeing. Atlas's halo was fractured into an evolving patchwork of asymmetry. Enhanced imaging traced the sources of this uneven look, narrow jets and plumes that erupted in specific directions. Dr. Tony Farnham at the University of Maryland mapped at least 4 distinct active regions on the surface, each with their own rhythm and composition. 2 vented steadily, while others fired intermittently like geysers on a timer. Perhaps most puzzling, several jets kept aiming in the same direction relative to the sun, suggesting either an extremely slow spin or a tendency for certain regions to wake up, preferentially based on solar heating geometry. Add the thermal story to the mix, and the mystery only deepened. Spitzer Space Telescope, in its final months before retirement, pointed its infrared detectors at the visitor and found Atlas running far warmer than physics predicted for its distance from the sun. University of Maryland's Dr. Michael Kelly analyzed the heat data and discovered its thermal inertia, essentially how well it holds and conducts heat, was almost 10 times higher than that of typical comet nuclei. That's asteroid territory, and not the porous, fluffy kind, but dense, metal-rich or heavily compacted material that responds quickly to sunlight. This hinted at either a nucleus riddled with conductive minerals or an internal structure compressed or altered in ways we haven't yet pinned down. Even the object's rotation refused to yield a straight answer. Months of photometric monitoring were intended to clock Atlas's spin rate, but the results bounced between competing scenarios. Dr. Ignacio Ferrin of the University of Antioquia, drawing on his experience with hundreds of comet rotations, applied advanced statistical modeling to the light curve. The outcome? Atlas might be spinning extremely slowly, over several days, or tumbling chaotically on multiple axes, or perhaps changing its spin state altogether under the torque of its own jets. Any one of those possibilities would carry different implications for its internal layout and history, but none could be nailed down conclusively. If the spin state is shifting in real time, that could point to ongoing structural change, subsurface cavities collapsing, large fragments breaking free, events that usually announce themselves through huge outbursts. Yet, Atlas offered no such dramatic flares beyond its strange bursts, leaving the cause unresolved. Put all of this together, and a strange picture emerges, an object active like a comet, but chemically and physically unlike any comet we know, warm and dense like certain asteroids, but far more volatile-rich than rocky bodies should be, morphologically complex, with an internal engine driving jets at odds with expected rotation. By every classification tool astronomers have, Atlas is a misfit. As NASA's Alan Stern, principal investigator of New Horizons, told colleagues during a conference talk, Atlas just doesn't check the boxes the way you expect, and that contradiction may be its most important contribution to science. Atlas is forcing a rethink of how we label small worlds and what we believe is possible in planetary science. We're staring at an object that ignores our tidy boxes, which means either the boxes are incomplete, or we're dealing with something truly without precedent, That sense of novelty only deepened when teams tried to rewind its path to a likely birthplace among the stars. Dr. Corin Baylor Jones at the Max Planck Institute for Astronomy led a state-of-the-art reconstruction using the best galactic dynamics available, a task that demanded exquisite precision, not only Atlas's present position and velocity, but the cumulative gravitational nudges it might have accumulated over a million-year voyage. His group drew on Gaia's vast catalogue, positions and motions for more than 1 billion stars, then integrated Atlas's trajectory backward while folding in stellar flybys that could have perturbed its route. The outcome was both fascinating and maddening. Unlike 2I/Borisov, which pointed back toward a neighborhood near the red dwarf Kruger 60 with modest confidence, Atlas refused to settle down. The models pointed toward the general direction of Lyra, yet uncertainties ballooned enough that dozens of potential parent systems stayed on the table. More troubling, the motion showed tiny but measurable departures from purely gravitational behavior that didn't line up cleanly with the observed outgassing. Those non-gravitational accelerations were small, but they also failed to correlate with brightness swings or gas indicators, hinting that forces outside standard comet modeling might be in play, or that outgassing was happening in directions or regimes our vantage point couldn't easily detect. Then machine learning added an unexpected twist. At the University of Chicago, Darrell Seligman trained neural networks on Atlas's blended dataset, photometry, spectra, and high-precision astrometry, to search for patterns that human analysts might miss. Periodic signals emerged across multiple timescales, from hours to weeks. A few lined up with familiar solar rhythms, the 27-day rotation of the Sun, hints tied to longer solar activity cycles, but others had no obvious astronomical anchor. One recurrent signal, at roughly 42.7 hours, popped up in independent datasets and pipelines, without matching any known local rotation or orbital period. Seligman was careful not to overstate it, flagging possible analysis artifacts or instrument systematics. Yet separate teams replicated several of the periodicities, suggesting they may be real even if their physical meaning remains elusive. Layer that onto everything else, and Atlas's enigma grew a little darker and a lot more interesting. Meanwhile, the hunt for more interstellar visitors accelerated with fresh code and sharper filters built from Atlas's lessons. The Catalina Sky Survey, one of NASA's workhorses for finding asteroids and comets, upgraded its software to flag objects with hyperbolic motion and unusually high speeds, the smoking gun for an origin beyond the Sun's grasp. Within weeks, they netted 3 candidates, though none were as provocative as Atlas. As Catalina's director Eric Christensen put it, speed is the discriminator. Local bodies are bound and capped by orbital dynamics. Extrasolar travelers exceed escape velocity and trace open arcs. But there's a catch. Identifying that difference demands multiple nights of clean observations to lock in the orbit, and fast movers don't sit still for long. On top of that, discovery is biased. Large, active visitors like Atlas announce themselves with bright chromae and striking profiles. Small or inactive crossers can slip through unseen, their dots of light indistinguishable from background stars. That skew means our current sample probably overrepresents the biggest, dustiest, most cooperative members of the population. The true spectrum, including inconspicuous drifters or engineered artifacts that minimize drag and shedding, could be hiding below our detection limits. That selection bias fed into the most controversial line of inquiry. Abraham Loeb continued to argue that the unusual traits of Oumuamua and Atlas justify a serious testable framework for discriminating natural from artificial origins. In a detailed analysis, his team proposed observational criteria that could point to technology rather than geology, shapes tuned for function rather than formed by erosion or aggregation, surface chemistries that don't fall out of known planetary or cometary processes, thermal behaviors implying internal heat sources or advanced materials, and most tellingly, accelerations or trajectory shifts that resist explanation by gravity and ordinary outgassing physics. Run through that lens, Atlas remained largely consistent with a natural comet, water activity, dust-rich coma, a hyperbolic flyby, yet several specifics pressed against the edges of conventional expectations. The skewed volatile mix, unusual thermal response, rapidly evolving morphology, and the small non-gravitational terms that didn't track activity, indicators kept it in a grey zone where nature still looks like the best bet, but not a slam dunk. Loeb emphasized the speculative nature of the claim and the bar for evidence, framing the work as hypothesis-driven science, lay out predictions, confront them with data, and let observations rule possibilities in or out. That's where Atlas ultimately pushes the field beyond rigid categories and into a regime where every line of evidence matters, every anomaly demands a check, and every bold idea earns its keep by surviving contact with the sky. The line captures the core of the Atlas debate. Prematurely discarding low probability, high impact hypotheses can blind us to transformative discoveries. In practice, that debate broadened into a re-examination of SETI itself, what we look for, how we look, and how we prepare to respond when something unexpected appears. Traditional SETI has centered on electromagnetic technosignatures, radio and laser transmissions, either intentionally sent or leaking from routine activity. But a growing camp argues that physical artifacts, including interstellar probes, may be at least as informative and in some scenarios more detectable. Jason Wright and colleagues frame technosignatures as any observable physical manifestation of engineering, emphasizing that some are longer-lived, less ambiguous, and detectable over greater distances than biosignatures or narrowcast radio signals. Signals disperse and fade with range and can be swamped by noise, whereas macroscopic objects can transport information and energy across interstellar space without radiative degradation, making probes a plausible, perhaps superior, exploration strategy for a civilization surveying nearby stars. This perspective elevates interstellar objects, like Atlas, from curiosities to potential contact opportunities, even if the prior odds of any one object being artificial are low. The cost-benefit calculus justifies careful, structured scrutiny because the upside is civilization-defining. That shift of emphasis exposes a readiness gap in policy and practice. SETI's long-standing post-detection principles, articulated under the International Academy of Astronautics, IAA, focus on signals, rapid public disclosure, independent verification, and broad international consultation before any reply is transmitted. But physical visits compress timelines. Interstellar objects arrive unannounced and remain characterizable for weeks to months, not years, eroding the luxury of extended deliberation. In response, IAA-related efforts have turned to adapting post-detection concepts to artifacts, criteria for evidentiary thresholds, standardized channels for sharing provisional determinations, and guardrails on attempted interaction or messaging until representative international bodies, often envisioned through the UN's COPUOS, can evaluate risks, methods, and intent. These frameworks struggle with asymmetric harms. A false positive undermines credibility and squanders resources, while a false negative forfeits a once-in-history discovery. Their common denominator is transparency, rapid verification, and restraint in unilateral response. Operationally, Atlas catalyzed method and infrastructure upgrades that now spill into broader astronomy. New image processing pipelines honed to tease weak signals from fast, faint targets are already improving studies of asteroids, comets, and exoplanets by extracting more information from limited photons. Spectroscopic workflows built to characterize sparse, noisy lines are raising the fidelity of small body composition catalogs across the solar system. Machine learning models trained on Atlas-era data, their anomaly detectors, spectral classifiers, and motion filters are now scanning archives for overlooked fast movers and triaging nightly alerts to surface the most unusual candidates for human review. These systems are designed to both expand the historical sample by recovering past visitors and to keep future observing cadences from being overwhelmed by false alarms, balancing sensitivity and specificity so that genuine anomalies rise to the top. The social layer matured as well. Informal, real-time data sharing during Atlas's campaign hardened into durable international networks, with common alert formats, mirrored repositories, and prearranged multi-longitude handoffs to maintain coverage on transient targets. Those channels are now repurposed across time-domain astronomy, supernovae, kilonovae, near-Earth object, alerts, accelerating coordinated follow-up, and standardizing public communication to reduce confusion while maintaining openness. All of this converges at the threshold of a discovery regime change, driven by the Vera C. Rubin Observatory. With an 8.4-meter mirror and a 3.2 gigapixel camera, Rubin's legacy survey of space and time will scan the entire visible sky roughly every 3 nights, producing a fire hose of alerts on moving and changing objects. Forecasts differ widely because our sample size is tiny, but even conservative studies anticipate a step change. Some analyses suggest on the order of approximately 1-2 interstellar objects per year, 15 across a decade, while other modeling exercises allow for much higher counts depending on actual size distributions and albedos. Rubin's cadence, depth, and automated alert brokering uniquely position it to catch fast, faint interstellar visitors that previous surveys missed, lifting detections from rare events to routine science. Routine, however, does not mean trivial. Hundreds of annual candidates would exceed the community's capacity for Atlas-level campaigns, creating a triage problem which visitors merit intensive spectroscopy, high-resolution imaging, or spacecraft targeting. The solution already taking shape layers machine learning atop human expertise. Real-time classifiers ingest initial photometry, motion vectors, colors, and crude activity proxies to score ISO likeness and anomaly, promoting outliers for rapid human vetting while providing baseline characterizations for the bulk. The same systems are being tuned to minimize missed long-shot candidates while avoiding alert fatigue, explicitly optimizing for the rare, high-value cases that could straddle the artificial-natural boundary. NASA's and ESA's technosignature efforts echo this strategy. Diversify modalities beyond radio, quantify detectability across a broad ichnoscale of technosignatures, and prioritize observations that maximize information gain under tight windows and limited resources. Policy, technology, and culture thus align around a pragmatic posture. Cast a wide net for both signals and artifacts. Verify rapidly and publicly. Avoid premature conclusions and reserve consequential decisions, especially messaging or physical interaction, for processes with broad international legitimacy. The Atlas experience showed that the community can mobilize at speed, build and share better tools, and keep curiosity tethered to evidence, even when the stakes feel existential. If Rubin delivers the expected flood of interstellar visitors, the field will finally have the statistics to tell whether Atlas-like anomalies are rare exceptions or the first hints of a diverse population, natural, engineered, or something in between. In that near future, the right questions become tractable. Do interstellar objects cluster in compositions and trajectories, or do a few persistently refuse natural explanations even after exhaustive checks? Can triage pipelines consistently elevate those outliers in time to marshal global assets, or even ready a fast interceptor when geometry cooperates? And should unmistakable techno-signatures emerge, non-gravitational accelerations or thermal behaviors, irreconcilable with physics, coupled to engineered morphology, the IAA-style protocols will be stress-tested in an artifact context, with the UN-linked norms of verification, openness and collective decision-making as the backbone of humanity's first response. Those preparations aren't just bureaucratic, they are how science preserves credibility while giving extraordinary possibilities a fair, disciplined hearing, exactly the stance the Atlas debaters argued for from the start. The breakthroughs sparked by Atlas had ripple effects far beyond the telescope dome. Several of the analytical methods first honed to chase this fast, fading wanderer could just as easily transform fields as far removed as medical diagnostics or high-precision industrial inspection. And as astronomical surveys march toward an era where spotting interstellar visitors becomes almost routine, the Atlas campaign feels less like a one-off adventure and more like a blueprint for the opportunities and complications that lie ahead. It proved these rare arrivals can deliver an unparalleled look into the chemistry and physics of alien star systems, reshaping how we think about planet formation and even the distribution of life's building blocks across the galaxy. But Atlas also reminded us that such objects don't always read from the standard script. They can defy expectations, test old theories, and exposed the edges of our observational toolkit. Its quirks made it fascinating, but also maddeningly resistant to quick or tidy classification, underscoring just how badly we need new analysis methods and innovative strategies for observing the next interstellar guest. Beyond the technical and scientific lessons, Atlas carried a deeper weight, a philosophical and cultural nudge to reconsider our position in the larger galactic web. Whether fashioned by nature or by intelligence, these visitors force us to see our solar system as part of a bigger, more tangled network than we've ever known. The public reaction underscored that impact. Never mind the usual press release astronomy story, the very strangeness of Atlas gripped imaginations on a global scale. People who might normally skip over an asteroid update were suddenly following orbital diagrams, debating spectroscopy results, and speculating about alien flybys. That intensity came at a cost. The same mystery that fueled fascination also lit the fuse for misunderstanding and overhype. For the scientists in the thick of it, the task was a constant balancing act. Keep the crowd engaged, but keep the facts straight. The tight observation window only added pressure. With so little time to collect and digest the data, every public update was a high-stakes decision about how to be transparent, without letting speculation outpace reality. Social media proved to be a double-edged instrument. On one side, platforms like Twitter/X offered a direct line from research teams to the world, allowing real-time posting of images, light curves, and early interpretations, a level of openness that previous generations of astronomers rarely experienced. On the other side, those same channels seeded and amplified conspiracy theories, unfounded explanations, and distorted readings of provisional findings. The Atlas campaign made it clear that astronomy in the social media era needs better-built communication strategies, ways to channel the speed, reach, and energy of online engagement, while buffering against the viral spread of misinformation. In the wake of the campaign, educators and outreach specialists began reshaping how they bring the public into these kinds of discoveries. The emphasis shifted toward telling the story of scientific investigation, showing how raw data slowly becomes tested knowledge, rather than delivering only final results stripped of the messy process behind them. By giving audiences a clearer picture of the work between mystery and answer, they hoped to make the public more comfortable with uncertainty. Financially, Atlas carried its own lessons. The observing effort pulled in major resources from observatories and agencies around the world, representing a sizable bet on a target with no guarantee of returning anything revolutionary. But the investment yielded dividends well beyond its original scope. The image processing refinements built to pull faint comet details from noisy backgrounds could be repurposed for MRI scans and satellite reconnaissance. Tweaks to spectroscopic analysis pipelines, originally to isolate unconventional gas signatures, found potential in environmental monitoring and materials testing. Even the cooperative infrastructure, the institutional trust, the operational links across countries and continents, had tangible economic and scientific value, paving the way for faster, more fluid coordination on future projects. As the glow of discovery faded and Atlas shrank from view, the high-tempo chase gave way to the quieter but equally vital phase, making sense of what we saw. Teams everywhere are now deep into sophisticated simulations, testing competing explanations against the constellation of measurements gathered during those few intense months. It's slower work with none of the adrenaline of a real-time sighting, but it's here that the deeper truths will surface. In the end, the verdict that will anchor Atlas's legacy hinges on what those models and RID analyses reveal. If it was indeed just a large, fast interstellar comet, it still delivered unprecedented detail on the makeup of solid bodies formed around other suns. If, however, the anomalies hold out against every conventional model, if some chemical, thermal, or dynamical clue refuses to reconcile, then Atlas could become something far rarer. The first confirmed engineered object ever detected from another star system. Such a finding would rank with the Apollo landings or the discovery of DNA in terms of changing humanity's sense of itself. Of course, there's a third outcome, the one we face most often in frontier science, that we might never know for certain. There are limits to what you can squeeze from a few months of data on something already halfway back to interstellar space. Some answers may be gone for good with the fading light, and that in itself is a reminder of the boundaries of both our senses and our instruments. As we wait for the next one, and keep dissecting this one, We can already see how Atlas broadened our view. It stretched the science, tested the research networks, and forced us to think bigger, stranger thoughts about what may be drifting through the dark between the stars. Whether it turns out to have been an alien scout, a cosmic iceberg, or something entirely unanticipated, the data it left behind will keep working on us. The analysis underway in labs and on supercomputers around the world is still peeling back layers from those precious weeks of observation. Each paper, each new model nudges us closer to the answer, or at least a sharper question. In that way, Atlas manages to be both a showcase of what modern astronomy can accomplish and a case study in its limits. Armed with remarkable detection tools and sophisticated analytical methods, we were able to capture and decode more information from this one fleeting object than any previous generation could have imagined. But we also learned that even in an age of global connectivity, rapid coordination, and massive data processing, the universe still delivers mysteries that resist final answers, and that might be exactly what keeps us looking up. It's humbling to admit, but even after everything we learned from Atlas, the same hard limits still frame our view: distances that dwarf lifetimes, clocks that refuse to slow, and data sets that are never quite as rich as the questions we want to ask. That's the real heart of this story, the long human reach toward understanding while standing in the dark, guided by a few stubborn points of light. Atlas reminded us that we're stitched into a larger fabric, not just a solar system but a circulating network of matter and energy, and maybe even intelligence, threading between suns over spans so vast they make history look like a heartbeat. Whether that connection proves to be purely physical or something deeper is still open, but knowing it might be there already shifts how we think about our place in all of this. There's one more layer to Atlas that demands attention: the possibility that it brushes against unseen physics. One idea explored by dark matter specialists is whether an object like Atlas, traveling for eons through regions of varying dark matter density, could pick up tiny cumulative signatures in its motion or makeup. The expectation wouldn't be fireworks, dark matter couples weakly, so the effects would be almost whisper quiet, millimeters per second of velocity drift integrated across millions of years, subtle enough to hide in the margins of our uncertainties. Yet that's exactly why interstellar travelers are special. They live the long experiment no lab can run, crossing magnetic domains, cosmic ray baths, and potential dark matter streams on a scale nothing in Earth orbit could sample. In that context, groups modeled Atlas's path through the galaxy, looking for systematic residuals, deviations that persist, when every known gravitational nudge and ordinary environmental force is accounted for. Hints emerged at the edge of detectability, small, repeatable mismatches that don't disappear when the usual suspects are removed. That doesn't clinch anything. It's exactly the territory where measurement errors and model assumptions can masquerade as new physics. But the pattern matters. If those offsets hold under stricter analyses and future visitors show the same fingerprints, we'd have a new probe of the invisible scaffold that holds galaxies together. If they wash out under better data, we'll have sharpened our tools for the next object. Either way, the exercise stretches our methods in the right direction. There's also a more provocative thread about physics. We don't yet know. Some researchers argue that genuinely advanced technologies might not advertise themselves as familiar alloys or radio beacons, but as behaviors that read impossible to our current frameworks. That's not a license to explain puzzles with magic. It's a reminder that past impossibilities, ball lightning, meteor falls, even magnetism, became ordinary once the theory caught up. The test is whether a new hypothesis makes predictions that survive contact with data. If an object's selective outgassing, thermal response, or organized coma patterns can be reproduced with natural models, the extraordinary claim retreats. If not, and if those signals recur across multiple visitors, then our frameworks deserve the pressure. That brings us to the structure in Atlas's changing appearance. The cometary activity is usually messy: chaotic jets, turbulent flows, and light curves that wobble with rotation and geometry. What drew attention here were coma patterns that looked too coherent for random sputtering, streams that maintained form longer than expected, jets that seemed to lock to solar orientation, and bursts that pulsed in a way that made the light curve look less like a simple spin signature and more like episodic switching. Natural mechanisms can organize flow, layered crusts that vent along fractures, crystalline dust that scatters light in distinctive ways, low thermal diffusivity that gates sublimation. But the persistence and rhythm are what keep modelers iterating. If geometry and grain physics explain it, the lesson is that we underestimated what ice and dust can do under alien conditions. If geometry fails, we keep digging. Zooming out, this is the right posture for the road ahead. Interstellar visitors are both samples and stress tests. Samples of materials forged under other suns, and stress tests for our assumptions. They push orbit fitting to include faint non-gravitational nudges without overfitting noise. They force photometry to reckon with jet-driven asymmetries and sub-micron grains that polarize light in unfamiliar ways. They make spectroscopy work harder at the edges of signal to noise. And they make communication harder and better, telling a true unfinished story in public, while resisting the gravity of sensational certainty. Maybe Atlas will settle into the ledger as a natural comet with unusual chemistry, a hot core, and a gift for keeping us guessing. Maybe a piece of its behavior will resist every natural explanation and seed a new branch of inquiry. Either way, it changes how we're prepared. The next object will arrive to a community that knows how to lock telescopes in hours, stack clean spectra before the fade, and triage anomalies fast enough to matter. The debates it sparked about dark matter signatures too small to see until they repeat, about how to recognize unfamiliar physics without declaring it, about what counts as evidence when the clock is ticking, those are upgrades to our operating system, not distractions. And that might be Atlas's most important message, not a conclusion, but a discipline. Stay open without credulity. Push models until they break, then fix the models, not the data. Accept that some mysteries will leave before they finish their sentence, and build the capacity to catch more of the next one's words. In the space between certainty and wonder is where the real work happens, and where our picture of the universe, and our place in it, keeps getting bigger. One of the most perplexing features of Atlas was the way its dust seemed to ignore the rules. In the vacuum between planets, the solar wind and interplanetary magnetic fields are constantly at work, scattering and randomizing anything thrown off a comet's surface. Under normal circumstances, any coherent structures in a coma should dissolve within hours, yet Atlas somehow held on to long, ribbon-like flows of dust, stretching tens of thousands of kilometers from its core, patterns that remained ordered far longer than they should have survived. To understand how this was possible, Dr. Gianrico Filacchione of Italy's National Institute for Astrophysics ran advanced simulations of dust motion in Atlas's environment. His work showed that keeping such tidy, extended streams intact would require one of two things. Either the dust grains themselves had unusual electrical properties that let them interact with the solar wind and magnetic fields in a way that preserved order, or there was some kind of active organizing mechanism inside the coma. The first idea, the electrostatic hypothesis, pointed to exotic surface charging, perhaps the result of centuries of cosmic ray bombardment during Atlas's long drift between stars. Such a treatment might have altered the grains so they behaved very differently from dust born in the solar system. The second possibility was more speculative. Some hidden process within Atlas could conceivably be controlling the dust, steering and shaping the flow. It might be natural, magnetic fields generated by subterranean electrical currents, for example, or, if one stretches the imagination, even engineered. If Atlas were somehow an artificial construct, Filacchione himself was careful to stress that nothing he'd seen proved the exotic option. Comets are messy, complicated bodies. There may be physical mechanisms at work inside them that we simply haven't encountered before. Still, when you stack Atlas's regimented dust streams alongside its odd chemistry, strange heat emission, and tiny but real deviations in its path, the cumulative picture strains against standard comet models. The seasoned astronomers, the situation carried a whiff of déjà vu in the late 1960s, when the first pulsars were found blasting perfect radio pulses into space like cosmic metronomes. There was nothing in the textbooks to explain them. For a brief moment, YGM, Little Green Men, was scrawled half-jokingly in observatory logbooks. Only later did pulsars find their rightful place in astrophysics, as natural, albeit extreme, stellar remnants. For Jill Tarter, former director of the SETI Institute, These parallels are instructive. Anomalies, she says, are the driver's seat of discovery. It doesn't matter if the endgame is a new natural phenomenon or something unprecedented. Grappling seriously with the unexplained is how science moves forward. An atlas is reminding everyone just how incomplete our categories might be when we're confronted with something truly novel. That incompleteness extends beyond astronomy. Max Tegmark at MIT calls cases like atlas stress tests for the scientific method itself. When the data won't fit the available boxes, we either make new boxes or realize our map of reality was missing an entire territory. Whether that expansion turns out to be subtle or revolutionary, the act of wrestling with anomalies forces progress. In practice, solving the atlas puzzle has demanded a rare breadth of expertise. Astrophysicists map the orbit. Planetary scientists model interior structure and dust behavior. Chemists decode its molecular signature. Computer scientists mine terabytes of survey data for hidden patterns. Even philosophers and anthropologists weigh in, framing questions about what discovery means and how humanity reacts to it. Sarah Seeger, known for leading interdisciplinary exoplanet teams at MIT, notes that each discipline spots different patterns. An astronomer might see a dynamical oddity, a chemist, a rogue molecule, and a data scientist, a statistical outlier. But it's only in the synthesis that the real breakthroughs happen. That diversity of thinking has side effects far beyond Atlas. Machine learning systems trained to recognize subtle anomalies in astronomical datasets are now being adapted for diagnosing diseases, detecting financial fraud, and tracking environmental changes. Image processing breakthroughs from the campaign are now informing military satellite reconnaissance, civilian Earth observation programs, and even the navigation systems in self-driving cars. Atlas's globally coordinated observing effort has become a template for crisis, scale collaboration, climate scientists studying fast, forming storms, epidemiologists mapping viral outbreaks, and geophysicists tracking earthquake aftershocks are all borrowing elements of the Atlas playbook. Rapid alerts, shared protocols, round-of-the-clock handoffs between teams on different continents. As the first anniversary of its discovery neared, the attention was formalized. Major conferences devoted full days to interstellar visitor science. The American Astronomical Society filled an entire track with Atlas papers, from orbital fit refinements and coma chemistry to speculative astrobiology. The International Astronomical Union stood up a dedicated working group charged with setting ground rules for naming, classifying, and sharing data on future objects of this kind. Atlas has also become a staple in classrooms. Grade school teachers use it to hook students on space science. High school physics courses pull its trajectory data into orbital mechanics labs. University seminars in planetary science, SETI, and astrobiology cite it as a living example of science under uncertainty. How data trickles in, how hypotheses shift, and how collaboration shapes the outcome. The public appetite hasn't let go either. Planetariums worldwide have built programs around interstellar visitors, providing ticket holders not just with vivid projections, but with near real-time updates as analyses evolve. The story's mix of mystery, rigor, and open questions makes it ideal for bridging professional science and public curiosity. A reminder that the most fascinating discoveries are often those where, for now, the answer is still out of reach. Museums leaned in with hands-on exhibits that let visitors poke through real Atlas data, compare spectra, tweak light curve models, and come away with their own conclusions about what this object might be. That do-it-yourself approach mirrored the energy in amateur communities, where many had already contributed images and astrometry during the discovery window. Forums dedicated to comets and minor planets lit up with debates over Atlas's chemistry, thermal behavior, and origin scenarios, blending rigorous analysis with the sense of wonder that pulled so many into astronomy in the first place. Citizen science kept evolving alongside that enthusiasm. New platforms invited broader participation, mixing clever game mechanics with machine learning so human pattern recognition could tackle real research problems at scale, from flagging galaxy morphologies and tracking NEOs to sifting for outliers that might hint at another interstellar visitor. That public surge carried into the funding landscape. Agencies saw rising numbers of proposals for wide-field surveys tuned to spot hyperbolic objects. population models of interstellar wanderers, and mission concepts to meet the next one head-on. In short order, interstellar visitor science turned into a bona fide subfield of planetary research with dedicated teams, specialized instrumentation, and targeted grant lines. Private players followed suit. Breakthrough Listen broadened its techno-signature search to systematically monitor interstellar objects for any artificial emissions, while space companies began studying rapid response intercept missions using increasingly capable robotic spacecraft. Commercial space changed the equation from the Oumuamua-era reusable launchers promised week-scale deployment rather than multi-year timelines, and advanced manufacturing shrank instruments to deliver lab-grade measurements without the mass penalties of old school payloads. The technology curve opened doors to bolder ideas. Studies explored constellations of small interceptors staged around the outer solar system to give early warning and fast flybys. Concepts for nuclear-powered probes aimed at velocity matching with truly fast interstellar targets. Even sample return scenarios were mapped out. The most ambitious of all, because returning material from another star system would transform arm-length astronomy into benchtop science. With samples in hand, isotopic ratios could reveal formation temperatures and stellar environments, microstructure could distinguish natural aggregation from engineered assembly, and trace chemistry might expose faint biosignatures or technosignatures that remote sensing would miss. None of that comes easy. The closing speeds demand propulsion that pushes beyond today's norms, whether that's nuclear thermal, high-power electric, or advanced solar sails that can pivot quickly from standby to intercept. The timelines force rapid decisions and pre-built playbooks, so missions can launch within a narrow window, and planetary protection cuts both ways. Protocols would be needed to prevent Earth contamination by truly alien material and to keep pristine samples free of terrestrial noise. Despite the hurdles, the scientific payoff is so high that serious design work is already underway. Teams at NASA JPL are exploring nuclear-enabled interceptors that could rendezvous and return, while ESA has begun framing joint architectures to spread cost, risk, and expertise across partner nations. As ambitions rose, so did the need for rules. Interstellar objects do not originate within any national jurisdiction, and the legal framework for studying, sampling, or altering them is largely unwritten. The UN Office for Outer Space Affairs opened preliminary talks to sketch international protocols tailored to interstellar targets, extending lessons from planetary protection and debris mitigation. Those discussions included more than agencies and labs, legal scholars, ethicists, and representatives from developing nations pressed for equitable access to results and a say in how these shared cosmic resources are handled. The thorniest edge cases revolved around artificiality. If an object like Atlas were proven engineered, would it be property, derelict, or heritage? Who could authorize contact, analysis, or reverse engineering? Those questions bleed into first, contact ethics, and the rights of non-human intelligence, moving from science fiction into policy planning, precisely because Atlas's anomalies showed how quickly speculation can turn into preparation. Astrobiology found fresh momentum too. Even in the fully natural scenario, Atlas's unusual chemistry and heating history pointed to diverse planet-forming environments beyond our own. The simple fact of water and complex organics in interstellar travelers implies that prebiotic ingredients might be spread widely through the Milky Way. Some researchers revisited panspermia as a long-shot mechanism for life's spread, with interstellar objects acting as carriers between systems. Most biologists remain skeptical that organisms could endure radiation doses and million-year voyages intact, but the non-zero possibility keeps the question alive, especially if future visitors deliver more detailed chemical evidence or someday returned samples. In that sense, each interstellar object is both a messenger and a test, a chance to refine models of how planets and life's chemistry take shape elsewhere, and a prompt to build the tools, policies, and collaborations needed to be ready when the next enigma appears on our doorstep. Even the most basic organic compounds or primitive pre-life chemical systems carried between star systems could, under the right conditions, seed the emergence of life on a welcoming world. That possibility gave interstellar visitors a weight far beyond their role as snapshots of planetary formation. They might also be couriers for life's starting materials. The astrobiological implications are profound enough that researchers have begun reshaping entire fields to account for them. In laboratories, biologists and chemists are now simulating the unforgiving conditions of deep space travel, extreme cold, cosmic radiation, vacuum, to test the endurance of hardy microorganisms and complex organics. These experiments keep delivering surprises. A handful of microbes and molecular systems handle the punishment far better than expected, suggesting that panspermia, the transfer of life's ingredients between solar systems, is more plausible than many once believed. Atlas's arrival also fed directly into mission planning for life detection probes, here at home and across the solar system. If alien organics arrive with some regularity, the chemical story of life may be more varied than our Earth-centric models predict. That's leading to subtle but important shifts in the search for biosignatures. Future Mars rovers, Europa landers, and missions to Titan and Enceladus are being redesigned to avoid missing biological patterns that could have interstellar origins. Meanwhile, exoplanet researchers are widening their own nets. If interstellar debris can influence young habitable worlds, then an alien planet's atmospheric fingerprints might bear the mark of chemistry seeded from afar. Instruments like the James Webb Space Telescope and the even more powerful observatories on its heels are now tasked with looking for unusual gas blends that could point to biology shaped by foreign chemistry. By the time scientists were deep into the 2026 analysis of Atlas's data, its legacy had crystallized, even as its true nature remained unknown. Whether purely natural or against the odds, something engineered, it had rewritten the rulebook for how we study small bodies, how we coordinate across nations, and how we frame the search for extraterrestrial life and intelligence. Atlas proved emphatically that our solar system is not a fenced-off outpost, but a junction in a galaxy-wide exchange of matter and energy, a flow that has likely been running for billions of years. This single visitor has reshaped thinking on planetary evolution, on life's possible origins, and on our place in the network of worlds. Its arrival was also a reality check. The universe still has the power to blindside us. Centuries of data collection and increasingly sophisticated models didn't prepare us for how many fronts of knowledge one object could challenge at once. That realization that we still live with enormous blind spots may be one of the most valuable outcomes of all. The truth about Atlas may remain partly veiled forever. The short observing window and the ceiling imposed by today's instruments mean that some mysteries will resist every effort to solve them. Yet the pursuit itself has already paid off, leaving behind better tools, deeper cooperation, and a hardened readiness for the next anomaly that crosses our sky. Whenever that happens, we'll step into the chase with sharper eyes, faster reflexes, and a clearer sense of just how big the unknown really is.